Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Adam Riess with us today. Hey, Adam.
How you doing?
I'm doing well. Fantastic, actually, on this August 24th of 2022. And I'm in Phoenix. We are getting a lot of rain this summer, much more than usual. And so where are you located at?
I'm in Baltimore, Maryland, on the campus of Johns Hopkins University. And it's a pretty sunny, muggy day, as we often get toward the end of August when you're hoping that, okay, it's time for this summer mugginess to end and for the cool fall to start, but not yet.
Soon, September. Although in Phoenix, we will stay hot until October before it begins to cool down here. But he'll cool down a little bit easier on the East Coast there. So awesome. Adam, what do you like to do for research?
I like to figure out how far away things are.
Well, very good.
And
anything in particular?
Yeah, stars, exploding stars, pulsating stars. And then I like to use that to measure the expansion history of the universe and learn what's in it.
Very cool. And that is going to bring us to this very awesome, and I'm going to talk about it for a minute, this very awesome APJ letter. And I want you, first of all, people, it's open access, so you can get it for free. Go get a copy. And number two, I do want you to note that this is a 52-page APJ letter. And this drives home the point that the primary metric for APJ letters is impact. It's not length, okay? Size, length is a secondary metric, but the most important is that the work will have impact. And if it does have impact, you can put in 52-page APJ letters. And so a comprehensive measurement of the local value of the Hubble constant with 1 kilometer per second per megaparsec uncertainty from the Hubble Space Telescope and the SHOES team. And Adam, take us away.
Sure. So this article is actually part of a special focus issue for APJ. So there's about another dozen papers involved from the SHOES and Pantheon Plus collaborations. So this is, I would say, a culmination of maybe a 15-year effort to measure the Hubble constant. The paper starts with a little history, and so I'll mention this history very briefly. I think everybody's familiar with the century-long quest to measure the Hubble constant. When the Hubble Space Telescope was launched, a couple of key projects or programs were set up to measure it. And I would refer to those as Generation 1 efforts. Their stated goals to measure the Hubble constant to 10% precision, which would sort of end this factor of 2 debate, 50 or 100. I think those programs were largely successful, and they used the first good camera on Hubble with PIC 2 to do most of that work. The SHOES program started out in the mid-2000s, around 2005, as a second-generation project. And its goal was to complement the improving quality of the cosmic microwave background data to provide a kind of bookend to the expansion history of the universe, with the CMB able to reach percent-level precision. You can best leverage that to learn about the universe by measuring the Hubble constant locally to comparable precision, approaching percent level.
Cool.
And so that's challenging, and it requires sort of rethinking of the process. It also required new cameras, which were installed on Hubble, the advanced camera, and then wide field camera 3 with a near infrared channel. These extended the range to which you could observe Cepheid variables, which are probably the gold standard tool for measuring distances within tens of megaparsecs. And so we developed a distance ladder that was defined to use really a lot of gold standard tools. So to use geometry, and I'll talk more about that, to measure the luminosities of Cepheid variables, and then to observe those in the hosts of type 1a supernovae, and of course type 1a supernovae all the way out into the Hubble flow. But the aspects that are different than the first generation was to reach that percent level precision, we had to really keep systematic errors low. And one of the key ways to do that is to make as many of the measurements purely differential as possible. And so what that means is mostly it means using the same telescope to measure the same kind of standard candle Cepheid variables across the distance ladder, so you could cancel out flux calibration as an uncertainty.
Good.
And the second aspect was to make our observations ultimately in the near infrared to reduce the impact of dust. The first generation was mostly optically based.
Yep.
And so that premise and pushing these cameras to reach greater distances was the basis of this. So if you can go to figure 1.
Let's take a look at figure 1. There we go.
That is showing you the basic 3-rung distance ladder shown there on the far left. And these are the different data sources that we are using. So for the first rung, where you use geometry to calibrate Cepheid variables, there have been a great number of advances in this in the past several years. Most importantly, probably Gaia, the Gaia mission, and parallax measurements. We're now up to the 3rd data release, and they've gotten quite good. And so we have observed the Cepheids in the Milky Way directly with the Hubble Space Telescope to tie those to the Gaia parallaxes. There's the famous water maser system in NGC 4258 that's been observed in the radio. Proper motion and acceleration gives you a geometric distance. And then there's been great improvements in the measurement of detached eclipsing binary systems in the Large Magellanic Cloud. So these all get you too close to 1% when you combine them. They're also independent from each other, so it allows you to do checks of, do you get the same answer with this one, or that one?
Oh, cool.
And then a lot of this work was in rung 2 in the measurement of Cepheids in type 1a supernova hosts. So back in the day, in generation 1, there were only a few type 1a supernovae that were in range. And those often harken back to 1937 and times like that when, to be honest, photometric measurements were not the best. So we have now reached 42 type 1a supernovae in 37 hosts, and all calibrated with modern detectors for the supernovae. And then we tie this to Pantheon Plus, which is a new iteration of this sort of the world's compilation of type 1a supernova data, but uniformly calibrated using large-scale surveys like Pan-STARRS and Sloan to tie these different photometric systems together.
Cool.
So if you move on to figure 2, this shows you the acquisition of all the HST data that was needed to make these measurements. And so some of the data goes all the way back 30 years or nearly 30 years to 1995, but most of it was obtained in the last 10 years or so using the new cameras. But for people who want to see where the data comes from, you could see that here. It's about 1,000 orbits at this point, which if you know HST, that's a lot of time. That's a lot. And so this time came to us through a series of about 18 competed proposals. So it was a sort of pay-as-you-go. And the collection of the type 1a supernovae can be seen in the inset graph, where, as I said, we started with a couple that we sort of inherited from the generation 1 experiments, and then we accrued over time.
Good growth there.
Yeah. So if you move on then to figure 3, okay, so lots of data tables. We released 10 to the 7 data numbers in this, and many sources. There's a compact form for just multilinear regressions, but the heart of the paper then is the discovery of Cepheid variables in these galaxies. So these are the new galaxies.
Cool.
In this paper, we more than doubled the sample from 2016, which was our last big update. Wherever you see a red dot is where we found a Cepheid variable. Cepheids tend to live around spiral arms and star-forming regions in late-tech galaxies. We also added more fields in NGC 4258, seen in the lower right there. The dots in red there are all new ones. The previously observed ones are the dots in white. And so because that's an important anchor of the distance ladder, it's important to have more Cepheids there. But again, this idea that you observe the Cepheids in either the first rung or the second rung with the same telescope. And so we've done that even in the Milky Way, where they're incredibly bright. We managed to do that. The way we do that is with using rapid spatial scanning to avoid saturation.
Okay.
If you go on to the next image, this is just a beautiful shot here. This is just the color images of all of these galaxies and the anchors. So this makes a nice poster. It's a poster in my office. And when people ask, could there be some difference between the galaxies in the anchor step or the second rung, you could look at them and see they're all basically massive spiral galaxies, whether it's the Milky Way, NGC 4258, these various hosts. That's the situation. Yeah. So if we could move on now to figure 5.
Yeah. There we go.
So the first question might be, how do you find type 1a? So excuse me, I'm so used to type 1a supernovae. How do you find Cepheid variables? And the answer is from their variability, from their light curves. And so you make observations over 11 or 12 epochs. You measure the photometry of everything you could see in the optical. And that's to identify them from their kind of sawtooth light curves. And this is a stack of all the Cepheid light curves in each of the host galaxies or anchor galaxies. And so you see this characteristic. These aren't just any variables. They're, as I said, sawtooth, the kind of asymmetric light curve that you see with the rapid rise and the slow decline. Now, we have so many light curves now and so many galaxies that we were able to do something really interesting to further probe this question of, are Cepheid variables in other galaxies like the ones in the Milky Way? So 100 years ago, Hertzsprung of the Hertzsprung-Russell diagram pointed out something called the Hertzsprung progression, which is a gradual change in the shape of the Cepheid light curves with period. And so if you go down to the next slide, figure 6, so in the lower line there is, as a function of period, those are specific examples of Cepheids in the Milky Way at 7.6 day period, 12, 16, 20, on and on, up to about 70 days. And what you see is the light curves change shape. They go from kind of, low amplitude symmetric to looking symmetric and taller amplitude to having the characteristic sawtooth that you see in the middle there, to having, again, a flatter amplitude as you go to longer periods. There's even little bumps like that where the blue arrow shows, you get a second resonance, a resonance between the second overtone oscillation and the fundamental. So these are characteristics of Milky Way Cepheids, but you cannot see these in any individual Cepheid light curve in distant ones because the signal to noise is too low. So what we did was we binned all the extragalactic Cepheids by period, and we run a spline through them, and you can recover, because we have enough statistics in the spline, you can recover the Hertzsprung progression. Very similar shape with period, including these small features. And these demonstrate, I think, to probably most people's satisfaction that these really are Cepheid variables. I think it would be surprising if it were otherwise. But since we have an interesting result on the Hubble constant, we want to keep checking the everything we can check.
Absolutely. That's fantastic. That's really cool.
Yeah. So if you move on then to figure 7.
Figure 7, we got.
Figure 7 is, so when we measure photometry of Cepheids, we throw down fake Cepheids in the data frames and at known magnitudes, and we recover them. And we measure the distribution of the fake Cepheids to verify first of all, to measure our uncertainties and then verify that they are Gaussian to, in this case, about 3 sigma, and also to measure any bias because the backgrounds are dense. And so you want to measure the background using artificial stars to get unbiased brightnesses. And so this is the results for each of the galaxies. And then if you move on to figure 8.
Figure 8.
So a question that often comes up is, how accurately can you measure the brightnesses of stars in fairly dense environments? And we provide 6 independent tests of the photometry in the face of crowding in the paper. This one is the most visual test, and so that's why I wanted to show this one.
Okay.
Here is the galaxy NGC 4258, and you can see that some Cepheids are found in fairly dense, crowded areas, like those two red ones that you see, right? So, you know, there are other things blended in there, and so you have to use PSF photometry to simultaneously fit the brightness of the Cepheid and all the other objects. In blue, there you see in the outskirts of the galaxy, a couple of Cepheids in very uncrowded regions where photometry is very simple to measure because there's nothing really around it. But the result is, after you make the measurements and do the artificial star measurements to measure the backgrounds of both of them, they should give the same distance to the galaxy, because after all, you know, the difference in distance between being, you know, in one part of the galaxy or the other is trivial, right?
Yeah.
And so if you go down, you look at the lower diagram, you can see to within 1/100th of a magnitude, the blue, which are all the Cepheids in those outer regions, compare very well to the red, which are the ones in the inner regions. This is only one of 5 tests of the internal accuracy of the photometry. Then if you move on.
Okay, very cool. Figure 8, figure 9, ancillary Cepheid data and not.
So these are then the period luminosity relations of the Cepheids in each of the host galaxies and the anchor. So for example, you know, if you look at the LMC, the upper left there, upper left. Yeah.
Yep.
So, you know, I mean, these are actually, even though they're very bright stars, they're still measured with the Hubble Space Telescope. And then you have the ones in all the various supernova hosts. So, you know, some yield more Cepheids than others, but, you know, in all cases, we were able to get some number of Cepheids.
And where's UGC 76? Okay, good.
So in all the hosts of 42 type 1a supernovae, and then if you move on, we also verify, this is kind of a boring plot, but we verify that the slopes we recover of the period luminosity relations are consistent with the sort of well-determined slopes very nearby, like in the Milky Way or the LMC or the SMC. But, you know, of course, they certainly get noisier, but we do a global fit to the whole period luminosity relationship so that there is one slope that's well-defined.
Okay.
You could move on then to figure 9.
Figure 11, maybe?
Figure 11, sorry.
Yeah,
figure
okay.
11. So this, you know, your eyes could glaze over, but I want to point out that we use a fully characterized covariance matrix for the data. So in the past, people would, you know, have uncertainty measurements for any object, the magnitude of a Cepheid or a type 1a supernova. But as we push towards 1%, we start to realize that there is covariance between measurements. That is, 2 Cepheids might live in the same galaxy, and if there's an error or uncertainty in the background of one of them, it is shared by the other one. And so one has to analyze the covariance then between the background estimates. And so these black boxes that you see along the diagonal there, right? Any black box there is a single galaxy. And the off-diagonal elements that you see there are the covariance of the, for example, the background estimates or maybe the metallicity estimates. So I should say for all the Cepheid variables, we measure the metallicities along the sort of radial gradient of each galaxy, and we index the metallicity of the Cepheid to its radius. We do that with H2 regions in these galaxies. So then those measurements obviously have covariance as well within a single galaxy. And then the Pantheon team has measured the covariance of supernova measurements. So the upper green box there in the upper right, that comes from the Pantheon team. And the red box, also that's the calibrator type 1a supernovae and the Hubble flow type 1a supernovae. So we then use that covariance matrix. And if you slide along, to the next figure, figure 12, Then we do simultaneous optimization. So this is probably the best known figure from the paper or from the SHU's collaboration, because this has been used in previous papers as well. This graphically shows essentially all the data in one place, which is essentially a 3-rung distance ladder. So, rung 1 there, geometry done many different ways, calibrates Cepheid variables, and you can see the residuals there. So that cloud of points you see in the lower left, in the those are individual parallaxes in the Milky Way from Gaia. And so that's why when you look at the residual plot there, the reason that that's a big green cloud there on the left versus the individual green dots on the right is, on the left, those are individual Cepheids. On the right, those are the sum or the average of all the Cepheids in one of those hosts using its geometric distance. So that's the difference there. When you average all those on the left, you do get to something of comparable or even better precision than those green dots on the right. And then if you move to the middle panel, this is the comparison of type 1a supernovae to Cepheid distances that essentially calibrates the type 1a supernovae. So there's 42 objects here now. So this is the big heavy lifting. This is where all the HST time went, essentially, was to make these measurements. And what's important is the scatter here between them. Listed there's 0.13 magnitudes. That's pretty much the scatter of type 1a supernovae as standard candles. And so it's really dominated by that. And then if you go to the upper right, this is nothing more than the Hubble diagram of type 1a supernovae. The red shows the range of redshift that we use to measure the Hubble constant. We go from about a redshift of 0.02 to 0.15. You don't want to go to too low a redshift because there are what we call peculiar motions or flows that would affect the measurement of the Hubble constant. And if you go to too high a redshift, you start to have importance in the change in the Hubble constant with redshift, that is knowledge of Q naught, the deceleration parameter, and J naught, or else you need to use a cosmology, omega matter, omega lambda. And we basically want to try to provide as close to a value of the Hubble constant that is as independent as possible of higher redshift information.
Good.
Okay, so if you move on then,
very nice.
So that's a visualization of the data, but in reality, if you go to figure 13, we do, lots of data tables. No, figure 14, sorry, one more.
Oh, good. Oh, good. Bayesian.
Yeah. So this is the usual kind of MCMC. Now, what we actually do is a multilinear regression. It doesn't require an MCMC. However, it's very useful for visualization to see how different parameters relate. So our fit basically has 5 global free parameters in the fit. 2 are the fiducial luminosity of our standard candles. So type 1a supernovae and Cepheids. 2 more parameters are the characterization of Cepheids in the form of the slope of the period luminosity relation and the dependence of Cepheid luminosity on metallicity. Okay, because that's measured. And the 5th parameter is the bottom row there is 5 log H naught. It's 5 log H naught because we make most measurements in magnitude. So that's the natural unit then in magnitudes. And so when you see one parameter with strong covariance, like for example, that one right there, that just says that there's a strong dependence of the Hubble constant on the fiducial luminosity you determine of type 1a supernovae, which of course makes sense because that helps set it. And so if you then slide on to figure 15,
money shot.
Yeah, this is probably the most important one in many ways. So if we do 100 million samples from our MCMC, we see, so our Hubble constant 73 plus or minus 1, but we really see that if you go out to 5 sigma tails, that's really where the Planck value lives. I should say Planck plus lambda CDM. And I really want to emphasize this. This is not a tension with Planck. This is a tension with the combination of using Planck and then translating the cosmological model and the expansion rate of the universe from redshift of 1,000 to essentially the present time.
Right.
And so, the cosmological model, vanilla lambda CDM, is most commonly used for that translation to describe how h of z, the expansion rate of time, will change over time. That is the Friedmann equation. And so what we find is that the value of the Hubble constant you would predict from the CMB data in concert with lambda CDM, which is about 67.4 plus or minus 0.5. That value is, that measurement is 5 sigma away from what we see locally.
Yes.
And this is a, I'm going to say, a now well-known phenomenon called the Hubble tension.
Yes.
And the interesting story, of course, is it's not just us who see it. It's not just Planck who sees their value in the early universe. The nature of the Hubble tension appears to be a confluence of measurements in the local universe that are between 70 and 75, but always higher than the Planck value, and a confluence of values that follow a similar route as Planck, that is, use the early universe, CMB measurements or BBN, to project with lambda CDM the value of the Hubble constant. And those range in the sort of around 67 to 68.
Yeah.
So this is very intriguing and very interesting to people because it suggests something interesting is going on.
Very nice.
Okay, so if you could now go to figure 18.
Figure 18, we'll slide on down.
Yeah,
18, there we go.
Out, just zoom, out just a little so we can see
a little more. There we go.
So the heart of the paper, I mean, it's you know, you can make a measurement, that's fine, but the question is, how robust is it? What are the systematics? And we spend a lot of time in the paper on systematics, and in particular, in the covariance matrix, we have put formally what people previously would have called systematics, like background or, you know, how metallicity affects things. We've formally put them now as part of our statistical error. And so that's in the error. And now these variants are outside the primary analysis. These are bifurcations, tests, questions, or other ways of analyzing the data. So for example, when I showed those, when I mentioned that we use 3 different geometric anchors, you could ask for the results you get from any one of them or any 2 of them. When you look at samples of supernovae, you could exclude different surveys. And all the time you're asking yourself this question, you know, is this one step or this one part driving the Hubble constant away from, let's say, the Planck value? That's the question that we have. And so going through all of these, including TRGB as a distance indicator, including M31, Cepheids, different ways of modeling peculiar velocities well into the Hubble flow. Any of these things we do, it is very hard to get the Hubble constant below about 72.5 or above about 73.5. If anything, I would say our baseline might be a little on the low side compared to where your sort of eye tells you the median of these things are. Right. That's okay. That's just sort of the way it comes out. And then as a last figure, if you go to figure 24.
Big 24. That's a nice one. Yes, this one. This one's nice.
Yeah. So, you know, as they say, this is not our first rodeo. We've been working on this project for, what's this show, about 15 years or so. And what this does is this breaks out the error terms or the error budget, going all the way back to the HST key project. So that's not our work, but that was the sort of first generation. So to put it in the same language, so you could see, you know, why did they have a 10% uncertainty? What terms drove that? And how did we get to where we are now? As I said, there's been tremendous improvement in knowledge of geometric distances. So going from the black bar back for the HST key project, that 5% was considered a consensus on the distance to the LMC. That was the consensus distance. What we have now, if you go down to, you know, all the way to the right there, is sub 1%. And that's based on the average of Gaia parallaxes, which are good to 1%. The NGC 4258 maser distance, which is about 1.5%, and the LMC detached eclipsing binaries, which are about 1.2%. And the other big piece of work is that kind of slate blue bar. Yeah. So that is the mean of the supernova calibrators.
Mm-hmm.
And so this has been the steady acquisition of supernova calibrators over time to get down to that point.
Cool.
And everything else at this point is smaller than that. They're significant, but they're smaller. The Hubble diagram of type 1a supernova itself, that kind of magenta color there, because there are so many type 1a supernovae in the Hubble flow, that is a very subdominant term as a result.
Yeah. Okay. Very cool.
Yeah.
Wow, it's really amazing the progression here of down to sub 1% at this point.
Yeah.
Very nice.
So all the error terms themselves are below 1%. When you combine them all, we're at that dash line, which is about 1.3, 1.4%. And that's where we are as of the present.
Very, very cool. Very nice. Adam, I want to thank you so much for walking us through this awesome APJ letter, 52 pages. Very cool. And let me ask, okay, so we're at the 1 kilometer per second per megaparsec range. So sort of where do we go with this? Let's say over the next 2 to 5 years. Is there stuff that JWST is going to be able to help knock that down? What are some of the steps maybe we can take to reduce some of the tension between Planck plus lambda CDM and local calibrators? So where do we go?
Yeah. So on the pure measurement side, the things I'm looking forward to are observations with JWST. So our group and other groups have time in cycle 1 to, I'm going to say, sort of repeat measurements made with HST, but with greater resolution, observed further to the red to even further mitigate dust. Those are important things to do. And, those observations will take, order a year or so to happen. And so we'll probably see the fruit from that in, year and a half to 2 years, sort of a thing. So that's exciting, and that should definitely happen. Gaia data release 4 and 5 will help as well, because we continue to chew away at the uncertainty that can be done geometrically with parallax. So those are things related to the kind of measurements I've been showing. LIGO, which has the ability to measure distances using standard sirens.
Okay.
These are gravitational wave sources. Is always been on our radar screen as something exciting and interesting. They had one event in 2017, this Kilonova event with an optical counterpart, and there the gravitational wave signature actually allows you to solve for the masses and determines the gravitational wave luminosity of the event and therefore the distance. The challenge, I would say, there has just been the rate of such events has been lower than people had hoped. We thought we might see a 3 or 5% measurement of the Hubble constant by now from LIGO. That still may be a few years off.
I think so. Yeah.
So that's what's going on the local side. On the early universe side, there are new CMB results that should come out over the next couple of years from ACT and SPT, which could be interesting, particularly because the last ACT release showed some evidence of something a little bit beyond the vanilla lambda CDM model, something called early dark energy, just showed a hint of it. But as we think about solutions to the Hubble tension, the most interesting possible solution, of course, would be something new about the universe that we were missing that would explain why lambda CDM is not connecting the early and the late. And so another episode of dark energy that's called early dark energy, another neutrino, something that pumps up the energy density in the early universe before recombination, essentially changes the sound horizon and recalibrates the cosmic microwave background and baryon acoustic oscillations, and in principle could bring things into agreement.
Cool. Well, this is going to be, even though we are down now at the 1 kilometer per second per megaparsec, it'll be really cool over the next couple of years to see this tension go away, to see some of the improvements. I think the gravitational wave is a very interesting one to go. It's very nice. Cool. Adam, thank you once again. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.